Hello, welcome to our talk on ray tracing the world of Assassin's Creed Shadows. I am Melino Kante, and presenting with me today is Luc Leblanc. We are respectively team lead and technical lead for Anvil's rendering team focused on lighting and ray tracing topics. Before we start our presentation today, it is only possible because of many years of work from our team and incredible collaborators, and I therefore want to thank them first. The Assassin's Creed games are systemic large-scale open worlds, and Assassin's Creed Shadows is our most dynamic one yet. Not only do we have dynamic transitions for time of day, we also have 14 unique weather states and 4 static seasons that have an impact on weather, materials, and time of day. Uniform probe solutions, uniform probe distribution solutions does not really scale well with these dynamism today. Therefore, the technique has evolved over the last years. For Assassin's Creed Origins, we have moved to a sparse solution instead, and for Shadows, we have developed the ray trace, diffuse, and specular solution. The need for scalability is more than just for world dynamism. We also need platform scalability, as a single platform today can also use 2 different solutions depending on the quality or performance mode chosen by the player. Before we start the talk, here's a quick video showcase of the environments we had to ship in Assassin's Creed Shadows. We've organized our talk in 2 main sections. First, you will deep dive with Luc into our RTGI algorithm and its implementation, in which we will detail as much as possible. You will notice that we cannot cover everything on the slides, as there is too much to talk otherwise. I will then present the challenges specific to Assassin's Creed Shadows, their source, and our solutions. Finally, we will conclude with performance, limitations of our implementation, limitations of the algorithm, and our planned future work. Without further ado, here is Luc.
Hello everyone, today I'm going to talk about the algorithm and its implementation details. First, the work that we're presenting today is based on techniques such as dynamic diffuse global illumination, the latest version with a per pixel ray tracing pass, and also using the probe volume as a cache for secondary hit GI computation. Similar system has already been present in game and used in games such as Metro Exodus and game running on the Snowdrop engine, Avatar, and Star Wars Outlaws. We'll look today at how we have implemented such a GI system to achieve the quality and the speed seen in Assassin's Creed Shadows, a large dynamic open world containing, among other things, a lot of vegetation and also running on multiple platforms. So let's start with a visual summary of the algorithm. First, we're going to rasterize the scene from the point of view of the camera, building a G-buffer and computing the direct lighting. What we really want is for each pixel to compute the indirect, diffuse, and specular illumination. In order to do so, for each pixel, we're going to select randomly a direction depending on the BRDF. We're going to do 2 passes, one for the diffuse lobe and one for the specular lobe. Then we cast a ray in the selected direction in the scene. In our system, we first start with screen space ray marching. We're doing it for multiple reasons. First of all, on some platform, console for example, it is faster to ray march than ray trace. Also, as you're going to see a bit later on, our ray tracing BVH world representation is very coarse for speed reason. And it doesn't contain every object in it. So in order to avoid self-intersection and also to bring back the missing information for the missing object, we're going to first use ray marching. And if we don't find any hit, we're going to then cast the ray into the BVH scene description. At the hit position found, either while ray marching or ray casting, we're going to compute the direct lighting coming from the sun in all the local lights. Then we're going to compute the indirect illumination contribution, only the diffuse part, with the help of a probe volume located all around the camera. The 8 nearest probes are going to be selected and interpolated to compute the indirect diffuse illumination at the it position. After doing so for all pixels, we're going to end up with a noisy solution that we're going to denoise and get our final lighting solution that we wanted. Now, to compute the indirect illumination at the secondary it, we use a probe volume that need to be computed beforehand. For each probe contained into the probe volume, we're going to cast some ray in all the directions covering all the surface of the probe. And compute the direct illumination at the it position, again from all the light source. And also after that, we're going to compute the indirect illumination using the probe volume, but this time we are going to use the probe result from the last frame, since we're currently computing the current frame result. This will give us multi-bound global illumination into our probe volume. This is the reagent's result after all the lighting of the probe. All probe will then be convolved to create a filter reagents cache, trading correctness for reduced noise to have a more stable result. Those probes will serve as a fallback when there's no geometry that's been hit. We also convolve all the probe with the diffuse BRDF to produce an irradiance diffuse cache. This one is going to be used to compute the indirect diffuse global illumination at any point in space. Now that we have finished looking at the overview of the algorithm, let's take a look at the ray tracing scene definition. As mentioned previously, our scene description used for ray tracing is a coarse representation of a rasterized version. This is for speed reasons. Since we have to throw a lot of rays into our scene description, we want them to be as fast as possible. In order to do so, we're going to use low-level LOD for the geometry, as low as possible without incurring visible artifact. Also, there's no vertex animation support, no skinning, so no character, or even moving vegetation. We're going to call as much as possible small geometry, such as small vegetation and small cluttering object. To speed up getting the it result back, we're going to bake some triangle data so that we don't need to first fetch the vertex indices and then fetch the vertex data associated to its indices and then interpolate that. We're just going to fetch the triangle data, interpolate its UV, and we're going to have everything we need. Using the same philosophy for the material, we're using a unified description for a material, contrary to what we use for our rasterized version, where each material can have its own shaders. This unified description allows us to use inline ray tracing, which is generally much faster on multiple platforms. For each material, we're going to compute some PBR constants, and that's what we're currently seeing on the screen. We also support texture in case of albedo and alpha to increase the quality of the result. The baking process for the material is pretty simple. We're just going to look at each texture of each PBR parameters, and we're going to compute an average value for it. In case of really complex material, like a tree planner, we first bake the result of the material into a texture class, and then use this texture class as input to our process. And we can use also directly this texture for the albedo and the roughness. In case of alpha material, we're going, of course, to take into account the alpha while averaging the value. But also we want to compute an opacity value for each mesh using it. So in order to do so, we're going to reproject each triangle of a mesh into the alpha texture and average the texels that are contained only inside each triangle and average those values. This parameter is going to be used later on for the ray tracing of the alpha test material. In case of material for vegetation, we add support for color lot. Different colors are defined according to the season. We also support alpha texture with two channels, one with and one without leaf, and the correct channel is selected again depending on the season. Each frame we're going to update our BVH representation. It's a pretty simple process. We add and remove instance depending on the streaming and the position of the camera. We also update the transformation matrix of the moving object. We support dynamic object, but just not vertex animation. We also update at the same time the terrain around the camera. The terrain is special cases. It's divided into patches, and we add and remove patch depending on the position. And the material of the terrain is also different. We have a necklace for each of the different PBR parameters for it. Finally, we're going to call the instance depending on the point of view of the camera. We're going to use time slicing since we have a lot of instances in our scene. We can have more than 100,000 instances. So each frame we're going to select a subset of it to call, and it takes approximately around 1 second to do the full scene update. Okay, so the next thing we do after updating our BVH is going to create and update our probe volume data. We use a standard definition of multiple cascaded 3D uniform grid following the camera. In Assassin's Creed Shadow, we have a bit more than 10,000 probe. Each probe has a data buffer information associated to it, but it has also some metadata. For example, a probe can have a whirl offset that allows the probe to move inside its region of definition to place it in a better position for rendering the scene around it. Probe data is stored into a texture class using octahedral encoding. We keep the result of the compressed gbuffer information, which will be used to compute a temporary buffer for the lighting. And this lighting buffer will be convolved, and we're going to generate a visibility probe for the computing weight for interpolation of the probe. We're going also to compute a filter reagents probe and a e-reagents probe, as seen previously. Updating all the probe every frame is going to be too costly, and we use different optimization to reduce the cost. First, we're going to update only a subset of the probe every frame. We also support 3 types of update. The first update is a full update where we cast Rave to compute the G-buffer. We're going to compute the lighting. We're going to convolve the results of the probe and try to move the probe if it's badly positioned. The second type of update is also a full update, but this time we support quarter resolution. This option allows us to have a speed gain of 40% for the ray tracing part while updating the G-buffer. And the third type of update is only updating the lighting, reusing the currently cached G-buffer information. We start the update by first selecting a subset of probe. In Assassin's Creed Shadow, we have a budget around 1,000 probe, or half of that, depending if we're running at 60 FPS mode, or if we're running on lower platforms, such as the Xbox Series S. We use a greedy algorithm in 3 steps to select the probe to update. In the first step, we select the newly created probe. Those are the probe that are created at the boundary of the grid when following the camera position. So on the opposite side, the probe will be deleted. Since the number of probe can vary a lot depending on the camera movement, it can vary from 0 to maybe 500. In order to optimize that and to stabilize the timing required, those probe are going to be doing the full update, but at quarter resolution. Then in the second step, we're going to select in each cascade a certain number of probe, approximately 16% of the remaining budget. That's going to be set in the second part. And we're going to select using a round robin scheme. That way, after a couple of frames, we'll be able to do the full update of each cascade. Those probe are going to be selected for a full update, but at full resolution this time around. Then we're going to do a third step of selection of probe. Again, like the second step, we're going to do a round robin selection on each cascade, but this time we're going to spend all the remaining budget. And those probe are going to be selected for lighting update only. And when the camera doesn't move that much, it's represent around 80% to 84% of the budget spent on one frame for the update. The first step done on all the selected probe is to update some of their metadata. We're going to classify the probe to be indoor or outdoor. You're going to see a bit later on why. And also we're going to classify the probe against the terrain. So those that are just under it will be moved above the terrain, and the rest that are too deep under it will just be disabled. Then for the selected probe, we're going to do the full update. So we're going to cast some rays to update the G buffer. We're going to trace the ray at the center of the pixel, so there's no jittering, there's no temporal accumulation. It doesn't really work well with our G buffer caching scheme. The maximum distance that we're going to cast the ray into the scene depend on the size of the region of definition of the probe. So if the probe is contained on a bigger cascade, we're going to cast the ray farther away, and if the cascade is smaller, then we're going to cast the ray at a smaller distance. When we hit some geometry, we're going to take all the material information and put it into the G buffer information of the probe. At the same time that we're computing the intersection, we're also keeping track of the number of backfacing that we hit. So that way, at the end of the update, when we try to move the probe if we need to, if we're not able to move the probe correctly and the probe is seeing too much backface, we're just going to disable the probe. As we're updating the G buffer, we're also going to compute the sun shadow and put it into the G buffer. It's not totally precise, as we can do multiple lighting updates before we are updating the G buffer, and the sun position can move during that time. With our probe selection algorithm, probe normally are being around fully the G buffer each 2 seconds. Since normally the sun doesn't move that much during that period of time, the approximation is good enough and give us interesting speed up. For the shadow computation, we're first going to look into a shadow map located around the camera, and if the hit position is contained outside of this shadow map, we're going to cast a shadow ray, only if the triangle is facing the sun. And then we're going to compute the cloud shadow and add that on top of that. In case of the sun is moving really fast, then updating just a small subset of the probe can lead to some weird result, and we can see really the lighting beyond update on a multiple frame basis. So in order to avoid that, what we do is first we're going to rescale all the probe lighting on the probe that are not going to be recompute this frame around. To compute the rescaling, what we do is we compute an approximation of the lighting. We take into account the sun position and the sky visibility and compute an approximation for the previous frame and then the current frame. We take the ratio between those two values and rescale the probe with this scaling factor. We don't need to rescale all the texel in all the probe. We only rescale a scaling factor contained in each probe. This scaling factor also helps to increase the precision of the probe, since each probe is in its own local lighting space. After that step, we're going to compute the lighting for all the selected probe, the one that we just traced and also the one that we did not, but we're going to use the cache G buffer. We split the computation in two passes, one for texel that have hit some geometry and one for the texel that didn't hit any geometry. Doing this split and also adding into the cost the classification pass give us a speed boost of 20%. In the first pass, we compute the direct lighting from all the lights and also the indirect illumination using the probe volume, irradiance probe volume from the previous frame. In the second pass, for the texel that did not hit any geometry, we're first going to try to use the probe radiance cache. If the end position of the ray is contained into the probe volume definition. If it's fall outside, then we're going to use a sky approximation texture containing the radiance of the sky. It's a pretty small texture, so the precision is not that much. At the end, we're going to output two values, and it's going to be the computed radiance, but also just the local light value. This way, when doing the convolution, we're going to end up with average radiance for the probe, but also an average local light illumination, and those values will be helpful to rescale the lighting for the probe that are not being computed. The next step is going to be doing the convolution on all the selected probe. First, we're going to compute a variance shadow map from the depth buffer. This will be used to compute weight for the probes when doing interpolation. One interesting point is that we need to rescale and clamp the value between 0 and 1 since we're encoding into 8 bits. But we do this rescaling and clamping before computing the average depth and average depth square. This helps reduce some leak in some cases, for example, in corner of rooms. We also convolve the radiance result to produce a filter radiance and an irradiance probe, as previously seen. During that process, we compute also multiple metadata information, such as the sky visibility, the average local light luminance, the average luminance. That's going to be the scaling factor for the probe. To optimize the convolution shader, what we're going to do is, well, each thread group is going to compute the result for one probe, and each thread is going to compute the convolution for one pixel of the output probe. While doing so, we first let all the thread participate into loading into the LDS shared memory the probe pixel. And while doing so, what we use is the bilinear filtering hardware query to fetch 4 texture samples at the same time. And then we're going to convolve that value. Doing so, we reduce by 4 the number of texels that need to be convolved, and we have a 4x speed up for that passes. But it's not totally correct since we're going to compute the convolution with the average value compared to the one for each texel, but the difference is minor compared to the speed boost that we get doing that. The last step of the probe volume update is to move the probe is to move the probe if the probe is contained inside the geometry or if the probe is contained too near some geometry. So what we're going to do is look at all the depth contained into the probe and figure out where is the minimum depth and the maximum depth, and if the minimum depth is negative or too small, we're going to try to move in the direction of the maximum depth value. And if we're not able to select a position where the probe is going to be far enough, we're just going to disable the probe and consider it invalid. Okay, so now that we have computed and updated our probe volume, we can now compute our per pixel illumination. We're first going to look at the diffuse illumination pass. For the diffuse lobe, we're going to cast a ray for each pixel in quarter resolution. It's enough to have a good quality, and we have a 4x speed up compared to casting a ray for each pixel. The ray direction is randomly chosen from a cosine distribution, and the maximum distance depends on the ray origin position. So the farther the position is from the camera, the farther that we're going to cast the ray from the camera. The first step is going to ray march the current screen to see if we find some hit. If we find some valid hit geometry on the screen, we're going to add this hit position inside a list of a valid hit list. And if we're able to fully ray march the full distance of the ray without hitting anything, we're going to add it to a miss list. So currently what you're seeing on the screen, the blue pixel are the miss pixel, and the green pixel are the one that hit some valid geometry on the screen. And for all the other case, we're going to need to cast the ray into the 3 BVH. So we're going to cast the ray, and again, if it hits some geometry, it's the green pixel, and add it to the valid hit list. And if it didn't hit anything, we're going to add to the miss list the blue pixel. And when we hit some valid geometry, we're going to build at the same time secondary hit G-buffer information with all the material, the normal information, the depth, distance from the ray, to be able to use in the next step for computing the lighting. Again, we're going to compute the lighting in 2 passes, looking at the valid hit list. It's pretty similar as the probe volume. The only difference is the way that we handle the sun shadow. Since now that we're rasterizing, we're casting ray from the point of view of the camera, we have access to cascade shadow map. So we're first going to try to use it. If the it position is contained and visible onto the screen, we're going to use the cascade shadow map. And if not, we're going to try to use the secondary shadow map, that is a shadow map position all around the camera. And if the it position fall outside of it, then in the diffuse case, we're going to just decide that it's fully shadow. It doesn't change really the lighting, and in this case, it doesn't leak any light. Then we're going to compute, after computing a shadow, we're going to compute the direct lighting from the sun and all the local light, and then compute the indirect illumination using the irradiance probe volume. Then we're going to do a second pass for the texel that didn't hit any geometry. It's pretty similar again to the probe what we're going to do for the probe volume. So we first try to use the radiance probe volume if the hit position is contained inside the volume, and if not, we'll use the sky approximation texture. So what we're seeing right now is the final lighting of the raycast from the point of view of the camera. Contrary to the probe volume, we're not going to output directly the radiance to be denoised. We're going to first encode it into a spherical harmonics. That way, we're going to try to reconstruct the full spherical radiance per pixel, and that's going to be denoised and upscaled later on. We're going to achieve much higher quality doing so. We also output the hit distance, that will be also denoised and filtered. This is going to produce a ray trace AO. That's going to be combined later on the result. And it's also this parameter is also helpful to help the denoiser to decide the size of the kernel that's going to be used, also the reprojection in case of specular lighting. After the lighting is done, we're going to run the denoiser to reconstruct the full indirect lighting. I'm not going to go into the detail of all the algorithm. It's pretty complex and it could be a course on its own. But we're using currently a modified version of the Snowdrop Engine denoiser that is based on the NVIDIA denoiser. We add a couple of modifications on top of that, specifically for Assassin's Creed Shadow. We're going to talk a bit about some of those modifications a bit later on. But I'm just going to say that this type of denoiser is really multiple pass, temporal and spatial filtering. And then finally, we're going to upscale from quarter resolution to full resolution using a bilateral upscaling algorithm with weight for the depth, the normal, and the material. And in this case, what we're upscaling is really the spherical harmonic, and then we end up with a per pixel spherical harmonic illumination that we're going to evaluate with the high resolution normal. Okay, so I'm just going to show you the benefit of using a spherical harmonic and not just filtering the raw radiance. So that's the output of the lighting, and this is the version that we obtain by just filtering the radiance, and we obtain the final irradiance per pixel. And this is the result while reconstructing and filtering the spherical harmonic. We gain much more detail and also better directionality in the lighting result. Okay, so now let's look at the indirect specular illumination. First, a word on the context of the development of this feature. It was first not planned for shipping in Assassin's Creed Shadow. It was planned to be added later on for a later game, but since we had a delay announced, we were giving 3 months to implement and debug and make it ready for shipping this feature. So we didn't have that much time, and we couldn't also modify the data on it, so we had to start from there, and we focused mostly on making it work and at a good quality. We did a bit of optimization, but not that much in that period of time. The algorithm is pretty similar to the per pixel pass, but it just we just add some specificity for the specular reflection, but also for increasing the quality of the result. Okay, so In the per pixel pass, we also support quarter resolution, but we support half resolution. That's half in width, but full resolution in height, and we also support full resolution. We end up shipping using the half resolution. That is the better quality performance ratio. So the first thing that we're going to do is select the direction a bit differently. We're going to use important sampling using a GGX visible normal distribution compared to just a diffuse lobe. Then the ray length that we're going to cast the ray, we're going to make it depend on the roughness. So if it's really rough and something really similar than a diffuse lobe, we're going to cast the ray really short rays. But if it's pretty reflective like a mirror, we're going to cast the ray really, really far away to get all the detail there. Since we're casting at least twice as much ray, is going to be twice as much slower, but in order to optimize, we decide to reuse the information that was computed previously in the diffuse pass. So in case of pixels that are really rough, above certain threshold, we're going to reuse the spherical harmonic per pixel that we have and just evaluate it at the wanted direction. We're going to use the same scheme when the ray is also really far from the perfect mirror reflection. In that cases, the weight of that pixel is going to be pretty low. So we're again just using the spherical harmonic evaluation. Doing so, we don't see that much difference visually, but we gain about 20 to 30% in speed up doing so. We also need to use a better remarching, so we're going to see much more the detail and the artifact produced by it. Okay, so as I said, we did a couple of optimization, but most of the modification were done for artifacts that were being seen in really specular material, for example, in water reflection. We did a lot of approximation on the diffuse part to make it fast, and those approximations are not really visible, but in the specular, they were starting to appear. So we needed to fix those. For example, we have an approximation for the alpha test material to make it faster to recast those. We're going to talk a bit later about it. But this approximation was really visible into the reflection. So we changed that to use alpha test texture to increase the quality. Also, the material definition that we use in our BVH is simpler. It's good enough for the diffuse, but in some case, when the reflection again is really mirror-like, we're going to see the difference in materials. So what we do is each time we have it from the BVH, we're going to reproject it into the screen, and if it's the same position and is valid, we're going to replace its material information by the G-buffer material definition, so that it's a bit higher quality. This is the difference that you gain. But since the difference is not that much, the line of demarcation between the G-buffer material and the screen buffer material is not that much visible, and normally you don't see it much. On the summary lighting, we compute a bit more complex lighting. We add the specular evaluation that was removed as a speed boost on the diffuse part. We also are going to add the shadow ray evaluation in some cases on higher platform. When the is falling outside the summary shadow map, we're going to cast some shadow ray and use it during the illumination, but only on INPC. On the mist part, first of all, we did some optimization. Around half the cost of the lighting evaluation is the probe interpolation. It needs to fetch and compute weight for 8 probes, and this is costly. So as an optimization that can be done, what we do is we only select the nearest probe at our it position, and we are going to compute its weight. And if the weight is high enough, we're going to decide that this probe is good and only use one probe. But if the weight of the probe is pretty low, we're going to decide this is an invalid probe and fall back to the 8th probe interpolation. Doing so, we optimize by, we double the speed of the cascade evaluation, of the probe evaluation. On the visual side, on the mist pass, we change the fallback texture for the sky to be a full local cube map that is following the camera position that is updated every frame. This cube map contains the terrain, the sky, and all the geometry that are far enough that are not contained into the BVH. Since again, on a pretty reflexive surface, we're going to see that we're missing a lot of geometry at the far distance. So that way, with the better fallback, we're going to add much more information. This is what we're seeing right now on the screen. Also on the lighting side of things, we add some fog evaluation into the specular lighting. And we don't do the fog evaluation onto the diffuse. It doesn't make that much difference, and it can be a bit more costly. But on the volumetric side, mostly on water surfaces, it can be very different, and it's much better looking, and it integrates much more better with the scene when we add the volumetric evaluation, like you're seeing currently on the screen. So on the left part is without the fog evaluation, and on the right is with the fog evaluation. Also, it's much difficult to denoise the specular result compared to the diffuse result, since the filter kernel that we're going to use is going to be much more small. The result will be much more difficult to denoise. So we use different techniques to help the denoising a bit. One of them is we're going to use demodulation of the region's result. We're going to demodulate the BRDF part, as explained in the NVIDIA NRD documentation. So when we do so, there's different way of doing it. We can just compute the regions and not take into account the BRDF into the equation, filter the regions. That way we don't have the noise coming from the BRDF. And then when the result is finally filtered, we can add multiply by the pre-integrate BRDF. That's normally what we do when we have screen space retracing and we have pre-filter local cube map. But when doing so, that's what we're seeing right now. At grazing angle, there's some cases when there's too much lighting. You can see it in the bigger part of the screen that is zoom in. So the best way to do it is to compute fully the regions computation and also the BRDF evaluation and filter that. But before filtering, we divide the result by the pre-integrate BRDF. So that way we reduce the noise for the BRDF part, so it gives a better result. And after denoising, we multiply back by the pre-integrate BRDF. And that's what we're having as a result. Another thing that we did to increase the quality, decrease the noise, is that we don't do the full denoising into the normal lighting space. We're going to compute the luminance. That way, there are sometimes cases, for example, when we are in an interior room, but it's looking outside of it. So some rays are hitting the interior value that are pretty low lighting, but some rays are going outside of it and they're really intense compared to the intensity of the interior volume, and it creates really noisy solution to denoise. So we do first we compress the space in which we're going to do the lighting. It's really not physically based, but it helps reduce the noise, and we have to ship without too much noise. Normally, when doing so, people use the Reinhardt tone mapping, but in our case, we saw that it really crushed too much the high level intensity, so we decided to just use a power function. The exponent that we use, I think it's 0.0625. Finally, we modify a bit the denoiser. Well, we specialize the denoiser for the specular part, but we also add some Firefly removal inside of the path. So one of the spatial filtering paths was already looking at all the pixels around it. So at the same time that we're doing that, we're computing the average luminance, and we compare it to the luminance of the current pixel that we're trying to denoise. And if the difference is too high between the average of the locality pixel, we're going to clamp the current value of the pixel luminance. And this is the result that we get doing that.
So now that we have covered our implementation, let's talk about challenges specific to Assassin's Creed Shadows. Alpha-tested material are known to be expensive. The reference material we will compare with the rest of our solutions here is using alpha-tested material and not having a limit on the number of tests we can do while tracing our BVH. The first step, of course, is then to limit the number of any hit calls that can be done. This results in about 85% of the cost on PC. But this biases a lot of result. We've tried limiting even further to reduce that occlusion added, and it is the solution we use for Specular GI, as the other solutions were too much of a glaring result, as you have seen before. If you have access to average opacity, you can use blue noise to instead use dithering and having a probability of the ray going through the BVH instead. This did not result in much performance gain on our end without limitation, and when limiting a number of any hit calls to 2, does improve slightly, but is very close to actually testing the material itself. The solution we have shipped for the diffuse solution for Assassin's Creed Shadows is using opaque approximation. We scale triangles according to the average opacity of the mesh and only use fully opaque intersections instead. With close results to n equals 2 on the alpha test, we actually get about 60% of the cost only. Here is the comparison between reference, the limitation on alpha test to 2, and the opaque approximation. As you can see, the results are very similar. Next, let's talk about translucency. Looking at this scene here, you can see that we are missing a lot of contributions from indirect lighting. Actually, just introducing indirect illumination from translucency will light up the scene. For direct lighting on the secondary hit, we evaluate for both faces the direct lighting and add them to the frame. For indirect lighting, we evaluate irradiance on both sides again, but instead of doing it twice, we classify the 8 nearest probes and split them according to the front and the back face. For direct lighting, for the primary hit when it is on the surface, we change the probability of choosing the front face and the back face according to the translucency. This modifies the PDF, which we have to accommodate. Finally, when encoding it for spherical harmonics, we flip the direction chosen to be front face aligned. Here is the result without any text. Now let's talk about light leaks. It is a well-known issue in real-time GI solutions, and we have split our main leak sources into both direct and indirect illumination. First, on the direct side, most of our leaking comes from CSM leaking. Actually, we have optimized occluders for our cascaded shadow map so that objects that are not visible or not projecting visible shadows in screen are not rendered. Our CSM also has a limited range, and objects too far away do not have in-shadow information. Finally, we have strong bias applied to our game, as walls are very thin in Assassin's Creed Shadows. So the secondary shadow map is our solution we have implemented. Since objects can be culled from the CSM in regions that are occluded on screen, we've added a low resolution shadow map that has all these occluders always rendered. We do a 1K by 1K resolution, about 64 meters around the player, and split it into 16 tiles, which we time slice update over 16 frame. We then apply the bias as we had for the CSM during the deferred lighting. We also do a min gather for the probes to even reduce these shadows even more. Finally, we also have cases where we are both outside the cascaded shadow map and the secondary shadow map, and they are considered shadowed to reduce the light leaks in probes. This causes issue, of course, in specular ray tracing, where we can have objects that are outside of the view and still in shadow in the reflections. On PC high quality modes, we enable the casting of shadow ray cast during the world tracing pass to alleviate this problem. For indirect lighting, our issue really comes from the fact that we are using 8 probes around their secondary hit, and some probes can be way too strong even though they are outdoor while we are indoor. Reducing leaks from outdoor probes in such situations is hard because the weights do not compensate strongly enough for the difference in lighting between both. Looking into our probe filtering, we offset our query position according to three well-known movements. We first do view direction offset, sampling direction offset, and finally the inverse ray direction offset. All are limited to about half the distance that our rays were traced. Then, to calculate the weight of any probe, we do first directional weight with wrap shading. We then evaluate the variance shadow map from the probe and take these weights and crush them if they were smaller than 2.2. Finally, we multiply these results by the trilinear interpolation weight. This is not quite enough as our visibility test is not precise enough. Outdoor probes are so much stronger than indoor that lighting can still happen. So we turned to using the indoor volumes that we use for a baked GI solution. This is a list of plane that lets us classify indoor and outdoor positions for our secondary hit and for the probes. We use also this volume to identify underground regions that are supposed to be kept valid for when under terrain. Finally, not showcased here, we have also added GI blockers for caves as the lighting was so low, blocking sky leaks was even more critical. Finally, we added a final step of occlusion which we call probe AO, which we are trying to represent the missing occlusion from inside the probe range when the distance traced by the ray is smaller than the range. So taking a grid spacing into account, if the hit distance is smaller, we will scale it accordingly. Now let's talk about occlusion. We will first start with the spherical harmonics result that you have seen earlier with Luc, and we will add the probe AO that will affect trees and the canopies. We then have a pass of ray traced ambient occlusions, which is similar to SSAO and is artistic driven. We also add a pass of GTAO, which is parameterized to bring back micro details and specific details lost from objects in our BVH, such as the character and clutter on the ground. Here is the results before with our full solution occlusion and the final image. Now let's talk about noise. We have adapted somewhat our denoising solution to specific challenge we have faced. First, with translucency, we had to add a specific mask for translucency as a same object could leak on its way itself when the material could be translucent on some areas and not on others. We also added another mask for character and vegetation to help denoising. When tracing at infinite distance for us and trying to reduce noise, we can see that interiors are still very noisy on our end. We have started using the probe radiance cache instead to trace shorter rays and fall back earlier on a radiance cache. This really helps us in performance, reducing high frequency detail, and since the cache is filtered and temporally stable, it helps keep the image in a much more stable state. In the end, it is a trade-off between precision and noise, as using this solution does bring in a lot of leaks. On the disocclusion side, we've tried using probe GI, which is our GI directly used from the probe, the nearest probe, for disoccluded pixels, but it gave too much resulting artifacts, we did not keep this solution. We have only added an extra spatial filtering pass that uses a Poisson filter with 8 or 16 samples for disoccluded pixels. We've also removed normal contribution weights for disocclusion on vegetation and relaxed the temporal reprojection criteria for moving vegetation. This really is our most noisy situation that we had to work on and is something we want to continue working on in the future. So here is the results of scenes with and without these fixes. So here in a dense forest, without and with all the occlusion, the translucency bringing in indirect lighting. Here in indoor with very noisy on the right and much more leaks on the left, and with our solutions is much more stable. Now let's talk about performance. First, our typical urban scene has about 2,000 objects in our BLAS and about 30,000 instances on our TLAS, for about 320 megs on the GPU. On the memory side, with the resolutions and the components we've shown earlier for the probes, we have about 73 megs allocated for around 10,000 probes. On the timing side, they have all been updated with this point of view in Osaka. As I will show, you have the total results and the paths if they are present on the async or graphic thread on the GPU. And also in orange, you have the results if no async thread is run at all and everything is run linearly on the GPU. You can notice also that for Xbox Series S, we have half the number of probes updated per frame for performance, and on PC, half also again, but because of frame rate. For diffuse GI timings, again, Xbox Series S is in a lower resolution because of performance. On the Specular GI timing, you can see here that we have only shipped on PS5 Pro and PC, and the timings are very costly, and this is because we have not the time to work on performance as much as we would like. So let's talk about limitations of our implementation. First, shipping two GI systems is very time consuming. Tailoring two different looks for technical directors for different contrast and GI results is very time expensive. Ray tracing materials is still very expensive in terms of user work, as complex shaders are not easy to be simplified by our current system. Lack of AO on objects not in BVH is very apparent, and we had to use solutions such as DGT-AO to compensate for that result. On our side, the ray tracing world quality is fixed. An object that is near from us in the BVH is the same quality as if it was at the edge of our BVH, and this causes issues on our side. Finally, we expect we have more disinclusion than we should have if we had 3D motion vectors. Talking about the algorithm itself, we do see the limitations of probe grid and buffer resolution on the detail side. We do see that adding more resolution and having more probes or smaller spacing could help, but these are expensive and do not really scale well with uniform probe distribution within the cascades. Next, probe interpolation always leaks, and we believe there is no good way to resolve leak proof with the current solution, as visibility is too complex to resolve with our current variance shadow maps. Screen tracing optimizations creates issues, of course, when the raster world differentiates from the VBH geometry. We've seen such cases where 50 centimeters were not enough because geometry were too different in some cases. Finally, complex cases are still noisy. We had to remove indoor volumes from basements in the castles of our game, as we prefer the leaks to having noisy and temporal errors. We do want to note that modern frames are upscaled and filtered for GI, and then upscaled again for the final result. And these have been taking a toll on the results for noise. So for our future work, we want to reduce production support load, so making it easier to ship using ray tracing, and we will automate more of our BVH construction. We want to hopefully get rid of all big techniques we have left for big GI and scale to lower platforms. As you can see, the performance for Xbox Series S is in the range of something that we can ship, but memory was not planned for this for Assassin's Creed Shadows. Next, we want to continue working on noise and leaks. We will implement importance sampling and investigate generating probes on surfaces and sparse cascades for a general probe solution. Finally, we haven't had the time to work as much on our denoising as we want, so we will look into our current denoising cost and making sure that they are reduced, as they are almost half the pass right now. Thank you very much for coming in for the talk today. Here are some final results. You can see that we have much more detail and less smearing of lighting values. Thank you.